Ooh, I'm fast.
I'm pretty sure you joined before I dropped the link.
I don't know how I did that.
That's pretty impressive. All
No,
right.
I know 100% how I did that.
Okay. It's like, yeah, I think you got in here before I dropped it. You must have got a notification that I hopped in the Zoom.
I saw, yeah.
Yeah.
Aw,
What's
a
up?
Yorkie.
Puppy.
Yeah, today's just gonna be kind of a relaxed after hours where we're just gonna kind of talk about, the stuff that we've gone over this week.
I'm assuming tomorrow's gonna be pretty straightforward.
It is. The sprint challenge for tomorrow, if you followed along at all this week, is going to be pretty straightforward. I don't
And if we
anticipate that
did
there's going
not,
to be a lot. Say again?
if we did not,
If you did not, then there may be a few holdups, but nothing too.
Taylor, you're smart. I think you'll do fine.
Yeah, I know, right?
I'm concerned about the vastness of at all. If you can follow along at all.
Well, it's intentionally open-ended because I don't know what constitutes a lot or a little for most people. Definitions tend to change. Yeah, so I guess, we can start with what's been what's the area where you feel like you are struggling the most, if you're comfortable talking about it. So we can
Understanding what hyperparameters to choose.
Okay.
I just feel like it's too much plug and play, and it seems almost too time consuming to be like, I don't feel like that would be something you'd ever do in the real world. It's just, oh, this hyperparameter worked all right, let's try another one, and then you run another 10, and then but
yeah, I second that.
Okay, so kind of understanding which hyperparameters to choose. Okay, what else?
The shapes of vertex, matrix, and stuff like that, and troubleshooting shape errors and stuff like that. Like a lot of people have been running into.
Okay.
Just knowing how the shape is supposed to be in correlation to what we're doing.
Gotcha. Okay.
So
how
that.
Shapes, how shapes work? Got it. Matrix shapes.
You just play around with it for 2 hours, Adrian. You'll get it.
Yeah, just flipping it, transposing it, not transposing it.
Yeah, I do that a lot too.
This goes with the hyperparams, but which loss functions are appropriate for what scenario?
Okay. Yeah, that works. I mean, a lot of them kind of almost have it in the name, though. So that's a good pickup. What in the world are you eating? Oh, it's a piece of paper. Yeah, he's just over there like, I'm going to eat some paper. Okay, so yeah, what loss functions to choose? Okay, anything else real quick before I start diving into something?
Yeah, just kind of overall what we're going to have to do tomorrow.
That's a good one.
Yeah, we'll do a dry run through the sprint challenge.
I mean, an example, something similar.
I mean, what you're going to be doing is you're going to be building a Keras deep learning model. Right. You'll be building both a simple perceptron and a multi-layer perceptron. You'll be given a logic problem that you have to solve, right? Using your machine learning model. You'll then, be prepared to be able to build a model and then get an accuracy score from it on, a classification problem, and then be able to report that accuracy and then do hyperparameter tuning and compare how your model performs. That is what I just explained to you, and doing hyperparameter tuning at the end there. That is the sprint challenge, right? Without giving you the questions.
Is it going to be like the basketball one?
What do you mean?
Steph Curry.
Yeah, Unit 2, Steph Curry. I know what you're talking about. But how do you mean similar?
We were just given the data set, and you try to get the best score.
I mean, to get the best score, it's more like demonstrating that you understand how to do these things.
Well, I mean,
you'd
have to do feature. I mean, it's not exactly the same, but
yeah.
If you didn't understand how to manipulate the features, you wouldn't have gotten the scores that you needed and stuff like that.
Well, you don't need to do any feature engineering. right?
Right.
That's not the focus. The focus, you should know how to do feature engineering, right?
Right.
We covered that in unit 2. No, the focus here is building the model, working the model, using the right methods from the model, right? Getting the information that it asks you for, and being able to present that. Okay. You do not have to use anything like TensorBoard or anything like that, though. I'll give you mad props if you do get some visualizations in there to kind of show how your models are performing, because that's a key skill, right? I think that's definitely useful.
Okay, yeah, but okay, that would be, I don't know if it's maybe just me, but I still struggle to interpret the visualizations, but that might just be because I've been like horridly absent this week. So I don't know if I'm the only one, then I'll deal with it by myself.
Well, whenever you train one of these models, okay, never mind. No, I misinterpreted the question. You said you're having a little bit of an issue, like understanding how to interpret the visualizations.
Yeah, I'm just seeing a bunch of lines and struggling to make sense of them, but but if that's not something that other people are confused about, then I can handle that later.
I think that's I mean, it goes along with.
TensorBoard.
Yeah, it goes along with the choosing the correct hyperparameters. I mean,
Okay,
I feel like
I guess,
context is
trying
relevant.
to use these lines to like pick hyperparameters to me isn't like, it doesn't click at the moment.
Okay.
He's
No,
like,
no,
oh, it's so
that's
easy.
good.
Look, I'm like, I don't know.
You're like, yeah, easy, totes. Not really. Okay, so yeah, okay, lot across the board. That's pretty cool. So let's start with the basics. I think the most basic fundamental question that I got was about matrix shapes, right? So if you guys recall, what constitutes legal or valid matrix multiplication, taking the dot product? What constitutes it being valid?
So the first two inside numbers have to be the same?
Yeah. And what do those two inside numbers represent? The what of the first matrix and the what of the second?
The column and the row. For the column from the first one and the row from the second.
Exactly. They have to, so the first matrix has to have matching number of columns to the number of rows in the second matrix, okay, which we call the transformation matrix. All right. So when you do this, so this is, okay, so whenever you're doing dot multiplication, or rather dot product, taking dot products of matrices, okay, you're doing, what's the word? Vector transformation, or matrix transformation, right? You are essentially creating a blueprint to warping in dimensional space, depending on the size of your matrices, okay? 3 Blue 1 Brown has a great video on that, but here's the part that answers the question. All right, if you have any number of weights, right, okay, to any number of inputs, then you need to make sure that when you're taking dot products, that you line up the columns of the first, which is usually the weights, to the rows of the second, which is usually the inputs, right? They need to match. If they don't match, you don't get the dot product, right? It just blows up at you and gives you the big red box that says, nope, that don't work. All right. Typically that error will look like, it's usually thrown by NumPy, and it says something like, input shapes do not match, or non-broadcastable array shapes, or something like that. I forget exactly what it says, but shape will definitely be in there, and you'll see, right, the shapes of the two matrices, and it'll be like, these don't match, right? So again, check the columns, and let's talk about what that is, because I think I actually gave out faulty information the other day when I was talking to my team about the arrays, right? Nested arrays, and the shape that they take. So hang on, let me pull this up real quick. Turn all that off. Okay. Hopefully you guys can see this. Let me see if it shows up. Hang on. Yeah, it does. Cool. All right, so you guys can see my my terminal window here. Okay. Yeah. All right. So if you have an array, okay, so I'm going to import NumPy. And we'll say that A equals MP dot array, right? 1, 2, 3. What is the shape of this array? Anybody know off the top of their head without thinking about it?
3 comma.
1 and 3.
1 and 3. I heard 1 and 3. What else?
Oh,
Remember, rows by columns. How many rows does this have?
Wasn't this one dimensional, so it would just be 3 comma?
Yeah, you
my
jumped ahead of me. I was trying to trick some folks up.
Oh.
Yeah, there's only one dimension, so there's only 3, right? If we're only counting in one dimension, we can only count the number of elements in this array. That would be 3, right? So the shape's going to be 3 comma because there is nothing that follows. So we look at a dot shape. We see that that is in fact the case, 3 comma. All right. So if we wanted to turn this into a 1 column, or rather, excuse me, 1 row by 3 column, right, where each element in the first array is an observation of a feature, right, then we would need to make this a multi-dimensional array. We need to add one more dimension. We need to add the index, so to speak, if you're thinking of this in terms of pandas. Okay, so we could say that A equals mp.array A. So now we're nesting A one more time in another array. This is going to add one more dimension to our A array. And we do see that now we have 1 row and 3 columns.
Is it like if you add another bracket, it's going to make another dimension?
Yes.
You have to just double
That's
the bracket.
Yep, double brackets. This is what we just did, just the long form way. All right. And the reason why I'm showing you this is because typically this occurs when dealing with the Y variable, right? And this method that I just showed you is one of the most common fixes that I have to apply to my code. Whenever I run my code and somehow, for some reason, I'm getting a shape error, it usually has to do with the Y variable, right? For some reason, you know, it's expecting a multi-dimensional array, but it doesn't have that second dimension of data, right? Doesn't know about that second dimension. So I need to go back and nest it one more time. Okay, so if you see a shape error and it's complaining that this is wrong and it's expecting something like this, then now you know how to fix it, right? That is probably the most common error that I've seen. Okay, so just a real quick recap. If I say B equals mp.array, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the shape of B?
This is 3 and 3.
You got it.
Like I'm confusing again something.
I made it a square matrix. I was trying to make it easy. Right, it's a 3 by 3. How many rows does it have? That's 3 rows, right? Each one of these arrays here inside is a row, and each value is a feature. So column 1 has the observations 1, 4, and 7. And column 2 has the observations 2, 5, and 8. Is that tracking? Makes sense, right? Then we can look at it like this, you know, we can print B and we'll get this nice, you know, vector or matrix representation. Makes it really easy to kind of visualize this.
Print A right now too.
Yeah. You see, we just get the 1 column, 1, 2, 3. Right. At its very core, that is how you can look at shapes of these arrays. So if you get data back and it's just in a bunch of arrays, right? That's not scary. You can work with that. It looks just like a pandas data frame. All you need to do is print it and you can see what it looks like, right? Take its shape and then you know how many rows and columns it has, right? That type of data is, you know, you can work with that. Okay, cool. So that's really all there is to shapes. I mean, typically you're not going to run into any other problems. You know, if you're trying to implement a step-by-step, you know, implementation of like a perceptron or something like that, and you're getting matrix multiplication errors when you're taking dot product, you know, either in your feed forward with your you're doing your weighted sum, I think it is, or when you are doing your back propagation, right? Trying to calculate your adjustments. If it's complaining that the shape of the array is wrong, look at the numbers, right? It may be that you just forgot to transpose, right? The X array. That's usually what the problem is there. Okay. Cool. So let's see. What was the next question that was worthwhile? Hyperparameter tuning. We wanted to know calculating loss. Okay, so these all kind of tie together, right? So I can kind of hit 3 birds with 1 stone, so to speak here. Yeah. So when you've got your model instantiated, and let's say we're just making a really simple perceptron, right? We've imported sequential. We model.add a dense layer with 1 output because we're doing a binary classification, and we have an input dimension of 2, right? So we're feeding in 2 numbers with 2 weights. We're hoping to get back a probability between 0 and 1, right? Using the sigmoid activation function. These are all terms that you should be comfortable with at this point. Let me know if you're not, because that's something I need to address. All right. So you've got your basic simple perceptron, which is a single layered neural network, right? It's got an input layer and an output layer, single perceptron. Okay. There's a number of things that take place, right? When we talk about these neural networks, there's 2 steps, right, to a perceptron model. What are they? Think about when we're training the model. What are the 2 steps that it goes through? Does anyone remember what those are from day 1? Okay. You have feed forward.
And bias. Wait, what? Sorry.
Weights and bias is features of the neural network, right? Okay. That's definitely components, I should say, components of the neural network. No, you have two steps. You have the feed forward step, which is where the data passes from the input to the output nodes. The linear combination occurs. The data passes through the activation function, and you get f of x as a return, right? Your activated output. Then you have what? What needs to happen at that point? What's the next?
Which makes the adjustments.
Back propagation, right? We're going to calculate an error using our loss function, right? It's going to give us an error metric, which we're then going to use to adjust the weights. Okay, so when we think about hyperparameters, what on this neural network, what components of this neural network can we make changes to that will alter? And let me rephrase this. What changes can we make that would most effectively alter, right, the way that it's going to function? What's the most obvious?
Altering the weight.
Well, okay, weights, but the weights represent what the computer is learning, right? We don't want to have anything to do with the weights, right? We want the computer to learn the weights, but we can tell the computer how to learn the weights, right? We can give it some sort of guidance. We just can't dictate exactly what a weight is, right? The computer's going to determine that. So how do we tell the computer how to learn a weight? What can we alter?
The activation function.
Activation function is something that we can alter, and that is definitely something that you would consider as a hyperparameter that you can tune 100%. On any given layer, you could tune any given hyperparameter or activation function to see how that affects the signal that's being passed from one layer to the next. But more specifically, what can we change that would affect how the model learns its weights?
It's a weight and its initializer.
Okay, so you have the random initialization of weights. That's what I'm hearing?
But there's like he drops the link with the parameters, and it was like you can kernel initializer, which is, it has like uniform or 0 or stuff like that. It was, if I got it right, like weight initializer.
Yeah, but without directly impacting the weights at all, or changing how the weights initialize, I'm looking for loss function. There you go. Yeah, I'm looking for loss function, right? If we change the way that the error is calculated, we can therefore, in turn, modify how the machine will learn these weights, right?
Just to clarify, the loss function is like a cost function. It's what the gradient descent is operating on.
Yes.
Okay.
It's part of that process.
Okay.
Very. Yeah, don't look at me and then bark. Stop. He's like looking at me like I'm gonna bark one more time, okay? Anyways,
It's
yeah.
a Chihuahua thing. I call it Tourette's.
It's just every time he hears a noise. Yeah. So you have your so you take this cost function, right? It tells you it's basically like a guide, so to speak, to the computer. Okay, make these changes to the numbers, right? Apply them backward through the model to the weights, right? And that gives us, combined with you got the loss function and the cost function. Those two things combined are going to directly impact the way that your model is going to interpret what changes need to be made to the weights on each iteration, right?
Right.
So, okay, now moving forward, right? So those are hyperparameters that you would think about. Also, you could change number of nodes in a hidden layer. Believe it or not, that's a hyperparameter that you can tune, right? Anything basically like that that you can change. Now, that being said, one of the things that people don't think to change or to iterate on is number of hidden layers. That's a thing you can change, right? So then you start changing the model architecture, though, which I think is a little outside of the scope of what we're doing. But I'm just trying to feed you a little nugget, right? Like, you know, there's more than just the hyperparameters that you can change about your model. Now, that being said, with hyperparameters, I think we pretty much covered the most important ones: number of nodes, activation function, cost function, and loss function. The way that your error is reported, validation, train and validation error, is going to change dependent on the type of problem that you have, right? If you have a binary classification problem, binary cross entropy is a very popular loss function. What is another loss function that you can use? Anybody know? Can you just name one for a
Categorical one?
Categorical cross entropy. Yeah, exactly.
Yeah, there you go.
Another take on the cross entropy algorithm. What's another? What's a one for a regression problem that you can use?
MSE.
MSE, right? Mean squared error. Pretty basic stuff. So you can Google search, right? Keras sequential loss functions, and I'm pretty sure it just gives you a whole list of them, right? Read through those. See what fits your problem. Right. Most of them have papers assigned to them. So when you get a chance, read the paper, find out what that thing's all about. I had the pleasure of having John Cody instruct me on how to by hand implement binary cross entropy into my perceptron model. That was pretty interesting, right? I was like, oh, it's actually not that hard.
Little side note: the search bar in the Keras
TensorFlow
documentation, yeah, is insane. Like it works really well. You can type in anything in that search bar and it'll find it within the documentation. So
I'm not telling you what to do, but you know, maybe having that open during your sprint challenge might be a boon, right? It would behoove you to make life a little bit easier for yourself, right? But you guys already worked through hyperparameter tuning. Grid search is a great way to do hyperparameter tuning. Keras has like a Keras tuner, I think it was, that I believe he showed you there at the very end of lecture today. That's just another option for doing, or you can do them by hand. Okay. Again, grid search is nothing but automating something that can be iterated on by hand. If you're not comfortable with doing a grid search and you want to, you know, iterate by hand, that's okay. Not as efficient, but you know, that's still technically hyperparameter tuning, right? So just be aware of that. And the reason why I'm saying stuff like that is because it's easy to get stuck on things like, oh, you know, how do I implement the grid search? Well, that's not important. What's important is that you're doing hyperparameter tuning, right? Doesn't necessarily require the grid search. You're just going to be doing a lot of copy pasting. All right. But yeah, hyperparameter tuning. What's the point of hyperparameter tuning? What are we trying to do?
to achieve the best model possible.
Right. We're trying to find the best possible model. So we just make iterations.
We're saving time and narrowing down where the best model could be. You're not going to necessarily find the best model off of the.
Well, I'm gonna revisit that one, but I don't think that it's saving time. It might actually be wasting time in some cases. But that is a return on investment type situation where you want to see, okay, I have this much time to get this much product, right? Or this good of a model, and it just becomes a balancing act, trying to weigh your resources versus, what kind of model, or you're, trying to solve your problem, basically. And that's why we stress MVP, because, typically when you get, into a real world situation, you have a limited amount of time, limited amount of resources. You need to get something, right? And then if it's working, but just needs a little bit of help, then you can pull some more resources and iterate again, right? But a lot of the time they're not going to want to, just throw everything in the kitchen sink at it first and not even know if it's going to actually do anything. Right? Could be a waste of time. Okay, a little bit of a tangent there. Back to Keras. So talking about, so when we do hyperparameter tuning, one of the best ways to kind of figure, or rather compare how well one iteration did compared to another iteration, right, is these graphs. Right? We can give ourselves some visualizations based on the history of the like the loss and the accuracy, right? Our scoring metric, right? Pop quiz. If loss is going down, what should your accuracy be doing?
Going up.
I see a couple fingers. Yep, going up. It should be going up, right? Typically what you want to see is that as your model begins to train and train well and starts learning the pattern, that you should start to see that, if this is your loss, right here, and this is your epics, right? As your epics increase, your loss should start to drop, right? And hopefully you see something like this, and it'll start to bottom out, right? This is what a good loss graph looks like, right? This means that over the course of a couple of epochs, your model was learning. Okay, now it's starting to plateau a little bit. It's not really learning much anymore, right? This is good. This is something that you want to see. If for any reason it looks different than this, you have made a mistake. It's pretty much the short of it, and or your data sucks, right? But if there's a pattern to be learned, if your model is learning something, this is what your loss will look like, right? And then in tangent with this, or rather in parallel, your accuracy to your epics, right? As epics increase, what's happening to your accuracy?
Increase.
Guys, starts to go up, right? We're hoping for something like this. What's interesting about these graphs?
Inverse.
Yeah, they're pretty much inverse, right? They're flipped. They're basically flipped over the Y, right? So as loss goes down, accuracy should be going up, same number of epics, right? This is an ideal type of model situation. I mean, real ideal would be like, oh, it only took one epic and now I have perfect accuracy. But you get what I mean, right? You're seeing an upward trend in motion. Okay, which leads me to early stopping, right? Would I want to stop my model here?
No.
Why not?
You're leaving a lot on the table.
Exactly, right? Not nearly enough epics to have really figured out. It hasn't narrowed down on the proper weights and bias, right? Still very high loss, very low accuracy. How about right here?
Could be better.
Okay, so it's definitely a lot better. Where the accuracy is up pretty high, and loss is pretty low. What's happening still? What is our tangent here?
Still far from 0.
Our slope is at the steepest, or not steepest. Rather, it's on the cusp. It's in the middle, right? It's not done yet, right? This tangent is still too high. There's still too much potential left in this model. Now, what about way over here?
Wasting a little bit of time and computing power.
Yeah, we've just wasted time, right? We probably had a good model right here that was just as good, right?
That's overfitting, yeah.
So so if I specify do 1,000 epochs, right? The model's going to just train 1,000 epochs. How can we stop wasting time doing unnecessary calculations?
Make sure the accuracy is increasing.
Make sure the accuracy is increasing, okay? What is that process called? It's called what?
Early stopping.
Early stopping.
Early stopping. Right? You can specify, okay, if we go 100, if we go 30 more epochs and the loss has not improved, right? Let's stop. Just quit. Right? Anyone remember working with XIGBoost? Or not XIGBoost, I'm thinking of XIGN game, never mind. XGBoost, right? Anyone remember XGBoost? Okay. Early stopping, right? Keep yourself from building unnecessary number of trees. If you weren't getting improvements, quit. Right? It's essentially the gist. And these things aren't perfect. They'll never be perfect. It's just not going to perfectly asymptote out here. What'll happen is you'll have a lot of jitter, right? And it might go up a little bit, go down a little bit. But if you're having a situation where it's like almost perfectly straight and then it goes up and then it goes down a little bit, but then up, but it never gets better than this, right? That's where you want to stop. This is it. We've got the model, right? So to get all the way out here, like, okay, it still hasn't improved, still hasn't improved, still hasn't improved. Okay, we got to 30 more iterations. This is still the best model. We're going back to this, right? That's what early stopping is doing. This makes sense to everybody? Pretty basic stuff.
I had one situation where my training looked like the one you drew.
Mhm.
Like my loss training looked like the one you drew, but my test looked completely different. It just looked like a squiggly line. Why is that?
Well, that's because who wants to take a stab at why that might be? His train did really well, but his test didn't. What happened?
Overfit.
He overfit. Right? You overfit on the training data. The model learned the training data so well that you gave it new data and it was like, I don't know what to do with this.
Oh, it was still good. It was getting good scores. It was just like at the bottom of my train, but just like a squiggly line. Like it wasn't a curve.
Well, I mean, yeah, that's what I was just talking
weird.
about. It's not going to be perfect. Usually it's not. Yeah, usually there's a little bit of jiggle, a little bit of jitter. That's due to what? Anybody want to take a stab at what that's due to? What causes that little bit of jitter? This is from Unit 1. This is a throwback to like day 2. Noise in the data. Right? You got a little bit of noisy data. There's not a perfect pattern. Right? The model can do only so well. Right? Doesn't predict the future. It just kind of does its best to statistically guess at about what should be, right? That was a turnaround. So the model's not going to be perfect, and typically, when you're working with your training data, you typically do have a pretty steep curve for loss and accuracy, and the training does look a little bit more jittery, right? It's because it's data it hasn't seen. Straight up, that's the reason why. The model doesn't get the opportunity to calculate adjustments on the training or testing data. So it's going to be a little bit more jittery.
And we could prevent overfitting by generalizing, right?
Generalizing. Yeah.
Okay.
There's a couple of ways you can generalize. Who wants to take a stab at 2? What are 2 ways you can help generalize a neural network? One also happens to be a hyperparameter you can tune.
Isn't early stopping considered one?
yeah, I guess early stopping would be, you can change the number of early stop, number of iterations or epochs. What's another?
Cross validation.
Cross validation. Okay. For your hyperparameter tuning, absolutely. Well, I'm looking for something a little bit more neural network specific. What can we do with neural networks that we can't really do with like a decision tree? That's going to help the model prevent it from overfitting.
Learning rate?
Learning rate. That's one. That is definitely one. You can modify the rate at which adjustments are applied, right? So if you run a model and it seems like it's overfitting, or it's like it'll either drastically overfit or drastically underfit, right? Or even worse, it'll just jump from one extreme to another, like I have with my Perceptron. Oh, real quick, slight tangent, but still on topic. Ryan, you remember the issue we were having with the my Perceptron class was predicting all zeros and all ones? Do you know what was required for me to fix that?
No.
Learning rate.
Oh, okay.
What was happening was the weights
Good question.
were being slammed from one extreme to another extreme because of the way the error was being calculated.
It was too high?
Yeah, it was going either too low or too high.
The learning rate was too high?
Yeah, well, the learning rate is 1, technically, by default, because just itself, right? That's the multiplicative identity.
I think I took mine out.
Yeah, but when I set my learning rate to 0.01, I was getting like 76% accuracy. It was, it was at least trying to solve the problem, right? It wasn't just predicting all zeros.
Yeah, I meant to ask Chris, because I gave him that code to see if he would get something similar to me, but it sounds like you got it, so.
Yeah, you just needed a learning rate. So I just straight slapped a learning rate in there, which just directly multiplied itself by the, what was it I multiplied it by? Oh, I have to pull it up later. Right, I just added a learning rate in there though, but the learning rate basically just changed the weight of the adjustments that were being back propagated.
What's crazy is I'm getting learning rate is not a legal parameter error right now. I think I know what's wrong with it.
Is it LR? It might be LR.
No, I forgot to put it in my create model.
Oh, okay.
What do you even change the learning rate?
It's in
Is it
model.
like a live code, like an example?
Uh,
I would even volunteer to do it, even though it would be a train wreck. But like, could we? I don't know.
yeah, I was to say the only reason I'm not doing it right now is because I can't do it right now. My computer's otherwise occupied. Do you want to load your stuff up?
I fixed it.
Yeah, did you?
I feel like there's probably a better option than me, though.
You're like anybody else, anybody at all.
It's past 9:30. My brain is already on the downward slope.
I don't have anything because I was absent the first 2 days, and then like yesterday I was doing a lot of business stuff. So today, so I've been just going through the lectures, and I don't even have any assignments done.
Oh boy.
You didn't miss much in the first 2 days. I would still recommend watching the lectures, but
that's what I heard. So the first 2 lectures I watched them, and now I've like kind of worked through the second 2. But
well, you guys might get an opportunity.
Yesterday, I would definitely recommend doing that one if it's anything. If tomorrow is anything like yesterday's assignment.
Yeah, that's the one I'm working on.
Okay, so apparently I didn't even do module 4. Okay, that's good. I'm looking through my GitHub right now. Like I didn't do assignment 4 at all. I didn't do assignment 3 either. Okay, I didn't do the assignments. That's not good.
Question when you're.
Oh boy.
Hold on.
I would share my screen. It's just loading though. I think I overloaded it. I crashed it a bunch this afternoon during the lecture.
Do you want to just walk me through one, or we can just?
Trying to see.
Walk you through, like I'm doing the Keras classifier right now.
Yeah, like we could just do a 0 to hero example would be like amazing for me, but
Yeah. Here, hang on one sec.
I mean, I don't mind showing you. A lot of the stuff he showed us was just copying and pasting what we did yesterday.
Yeah. Okay. That's basically.
But he did show us a different way today on how to do the sequential model, because before we were kind of like making almost like a pipeline. Oh, there it goes. And then today he did a model.add, which I see like from a bunch of other examples. I'm having trouble understanding why you would necessarily do it that way.
They're equivalent if you're talking about building it in the constructor or
Yeah.
model.add. Exactly the same.
Well, okay, but one of them you have to create whatchamajigger for. Oh my gosh, my brain.
Oh, what's
Flatten
your majigger?
layer?
Yeah, well, it goes what?
A flatten layer or what?
No. You define like create model function, and the other one you're just like creating a pipeline, right?
Okay, yeah.
Gotcha.
I don't know if that made any sense.
I'm getting
Like with the dense. Wait, what is dense?
dense means a fully connected layer. So
Okay.
that means every input neuron is connected to every other neuron.
No, you don't
in the
have to.
next
Never
layer.
mind. I just answered my own question.
Dense. Then you
Yeah,
have-
and I'm getting Jupyter Lab booted up. So give me just a minute and we'll do like a quick Keras model. I just got to make sure this works. TensorFlow.
Can you answer a question in the meantime, or you want to do it after?
Yeah, I can try.
Why is a perceptron not good at an XOR gate?
Why is a simple perceptron not
Sure.
able to solve the XOR gate? Because it does not have the necessary amount of complexity. You need one hidden layer with at least 2 neurons to solve the XOR gate.
What does the hidden layer add to the ability to solve?
So there is, okay, real quick, while I try to figure out why my computer thinks I don't have TensorFlow installed, this is part of the reason why I didn't volunteer to do live coding right away.
Do a Colab book.
I could also do it too, but I mean, it would just be a train wreck. So
Okay,
if you need it, I'm down.
in its most basic form, just imagine for a moment that this is 0, okay, and this is 1. Okay, the XOR gate, or rather an XAND gate, has values. Let's see, I think they are here and here, right, or something like that. Can you draw a line to separate these two groups, these two dots?
Yes.
Can you straight line? Okay. If I put a dot here and a dot here, can you draw one straight line to separate all 4 of these dots?
No.
No, you absolutely cannot. That's an XOR gate. Can you do it with 2 lines?
Whoa. Where
Yeah.
did you learn this? Is this like from comp sci?
No, but you can with 2 lines. 1 line, you can only ever get 50%, right? But if you make 2 lines, now you can get 100.
That actually helps a lot.
Yeah, makes a lot of sense.
Layer
So, like,
1,
what do you mean?
layer 1, layer 2. That's what they do. All right, this is your one of these lines will be your input layer with its weights, right? Trying to make a line. The other one's going to be the hidden layer with its weights, making another line, another linear divide. Right? That is at its core why you need at least one hidden layer to solve. Like obviously you could make a whole bunch more lines, but you're not gaining anything from that, right? You really only need the 2 to solve this problem. Right? Over complexity. Yeah, that's why. Because you can't be drawing no lines. Doesn't work. Can't cut 4 dots with 1 line. I'm sure there's a ninja out there who will beg to differ with me. Like I can definitely divide all of those 4 dots with one cut, but no, you can't do it with math. Yeah, I guess I'm going to have to go to Colab.
Stretch time. I keep getting the same like my models just don't do anything. I just get one number.
What are you talking about?
Here, I'll share. I'll share my crappy code. Where's
Like,
that?
what you talking about?
I think that's-
Like one number for the prediction every time?
I'll show my whole screen.
Do it.
All right, right here.
Okay, so your mean stays the same, your standard deviation stays the same. What is it that you're trying to do? The mean and the standard deviation shouldn't change.
Get a better.
Where's your what loss function are you using?
Oh, I don't even remember. Binary.
Okay, so where's your loss showing up at?
I don't think it shows. I don't think it shows on the grid share. It's grid.
Yeah, so you have no idea.
Right.
Mean and the standard deviation shouldn't change. They're static values for the data.
No.
Right.
Well, I mean it. I mean it changed here.
Wait, what? Means standard deviation. Okay, well I see that your bat size changes, your epics are staying the same,
Yep.
your learning rate's changing,
I mean, I got all that's changing.
but you're okay.
I mean, the same thing happened up here too. I guess this isn't too bad.
Could be no, that's normal. That's very normal. Could just have to do with the data. Is this the same data in the left one as the right one?
No. This is the diabetes, I believe. I don't even remember.
Okay, then it might
Yeah,
just be
the
a
diabetes one.
okay. Maybe it's a factor of the data that you're using. For some reason, the means and the standard deviation aren't changing. I
I
guess.
honestly don't even remember what the data is.
I mean, are you doing different? Are you doing
It's the telecom customer.
Because I'm thinking that probably what's happening is you're getting different sections of data. Like the only reason I can think that means and standard deviation is going to change. I'm trying to figure out where's that coming from, anyways. STD test score, mean test score. Oh, it's taking the mean of the test score and the standard deviation of the test score. I see. Okay, no, never mind. That means that your test score is not changing.
Okay.
So check to see, like I don't know what data you're running this model on.
It's the homework. I don't even know what it is though. It's the telecom customer.
Yeah. Okay. So it seems like your scores are not changing. Your test score is not changing at all. So every time it gets the mean of the test scores, it's the same.
It kept getting mad at me because it was an object too, but I didn't change anything.
Yeah.
I just kept tuning stuff until it worked.
Yeah. But that's still a pretty common thing. Like you'll see that these last three are the same. Right here.
Yeah. Okay.
Right. So I don't think that that's necessarily a bad thing.
Well, I mean, isn't the point to use the grid search to find the best learning rates and stuff like that?
What's your best? Take a look at your what's your okay. So you're
They're all the same. It doesn't matter. It says my best is 20, 32, and it's the first ones because obviously
they're all the same. Yeah. So apparently, whatever. I mean, I don't personally know because I didn't like I don't know about the report results.
I just figured I was doing something. I just felt like I was doing something wrong up here because obviously it's working.
Mm-hmm.
Why is your last layer softmax?
Yeah. What's going on with that? I just noticed it.
Oh, I don't know.
Change that to sigmoid. What type of problem do you have? Let's start there. Actually,
it's a binary classifier.
Yeah, you softmax isn't going to work. that's probably part of the problem. Let's take a look, see what it does.
See, that's the stuff I don't know. That's the stuff. Just like what I don't know.
Softmax equals multi-class classification only. Okay. That's it. Sigmoid, tanh. Sigmoid doesn't require any change in how you determine whether it's a positive or negative class, right? It's 0, it's negative, it's 1, it's positive, right? Pretty simple. However, if you do something like tan H, then -1 becomes, right? If it's less than 0, it's negative. If it's greater than 0, it's positive class. Does that make sense? You're taking the halfway point. Make sense?
No, it absolutely does.
But you're able to go all the way to -1 and +1. So, different activation functions. Excerpt from Tuesday assignment, build TensorFlow. Hang on, I've still got my pen. There we go.
Real talk, anyone that's been listening, or anyone that's still here. Oh, I crashed my browser. This has been my go-to listening when it works for the past week.
Dude, can you chill? Oh, okay. Tell me how you really feel. He's like, I just told you. Lo-fi hip-hop radio? Yeah?
Yeah, my computer is dying right now. Just I can't do anything. There we go.
Hey, man, I love lo-fi hip-hop radio.
Maybe you should switch to NW -3 or something.
Yeah, you need to open up one core, man.
This is Colab. It's not even my computer. It doesn't matter.
Oh yeah, that's true.
Okay.
Hey, I learned 100%.
That's not good. That's suspect. That's extremely suspect. Okay. Keep playing with that. I mean, the implementation is right. The implementation is definitely right. Yeah, you need to switch to a GPU. It's just, what are you doing?
I know. I just thought of that.
Taking so much time. Okay, so to kind of hit on this, what kind of architecture decisions could we make to avoid the problems the XOR dataset presents at scale? Are you able to achieve the same results as the bigger architecture in the first part of the assignment? Why is this disparity the case? What properties of the XOR dataset would cause this disparity?
Well, the non-single linearly separable part was the disparity.
Yeah, we figured out what the disparity was, because you can't separate all of the possible class combinations, right? All the possible XY combinations with one layer, right?
You know about that, Taylor, right? Running the runtime, changing runtime to the GPU.
Is this the modified XOR data set?
Yeah, so that it runs, yeah. Thank you.
It's at the top, it says XOR-ish data set above. What is XOR-ish?
Me?
No, I'm talking about the Zoom chat.
Did I say that?
No, C did.
Oh.
What does XOR-ish mean? Is it a modified XOR data set?
No, it was just the data set. It was picture. We were supposed to write it down. It was, I think, 3 columns and 7 observations or stuff like that. I mean, I don't know, maybe it's just sarcastic way, but because it's how it's written in a notebook, assignment notebook,
It's because the data had 1 extra column in it. That was noise.
Ah, okay. Yeah, all right. So it's asking what kind of architecture decisions could we make to avoid the problems the XOR dataset presents at scale? Add another hidden layer. Filter out noise.
It's the way it's raised, extrapolate this behavior on a much larger data set in terms of features. Like I'm saying, is this a matter of features? Is it a matter of dimensionality that you need more layers for a higher dimension problem? Is there a relationship between the number of the dimensionality and like how
Not
much?
always. Not always. Yeah, not always. It's not always a one-to-one relationship. Oh, I have 13 features, so I have 13 hidden layers. Right, like that's not how that works. I think when I had a pretty successful model that I built using a 64328848 multi-layer perceptron. that was kicking about 86% accuracy on the diabetes data set. So, I mean, it's difficult to describe, but I'm going to try to describe it anyway.
Was that yesterday's?
This assignment's Tuesday.
Yeah.
Okay, yeah.
Ryan, would you mind stop sharing
shit.
for just a moment?
I didn't realize I was still sharing.
I'm going to attempt, and probably attempt badly, to talk about one of the ways that you can go about attempting to decide how many hidden layers you want to use. Okay, so remember the XOR gate. All right, you have XY combinations that essentially for x equals 1, you can have y equals 0 and 1, right? Or for x equals 0, you can have y equals 0 and y equals 1. And for x equals 1, you can have y equals 0 and x equals, or y equals 1, right? This is not solvable with a single layer perceptron because there is no line. Imagine these are all one single line. None of these lines individually split all 4 groups, right? It's not possible. Cannot be done, right? You need a squiggly line, which is a thing, by the way. I'm not going to get into that. There is a squiggly line function. We're not going to do that. Okay, you need 2. You need 2. You need one layer.
Yeah, and the squiggly line function wouldn't work with a weight, an input, and a bias.
You got it. Yeah, you can't. That's why I said I'm not going to go into that, because that's a whole nother architecture.
But that can happen. There are neural networks like that.
I believe I'm not qualified to give an answer to that question.
Okay, I'll look it up.
Anyways, so you have, if this is the line, okay, one layer perceptron. How many groupings do I have here? How many total groups does this line create? 2. How many does this create?
4.
No, that's a trick question. 2. Top and bottom. And this is effectively what we have just created. Now, there's a reason why I'm showing you this, okay? Because geometrically, all we're doing is saying we need to cut this first into 2 halves, left and right, and then again in 2 halves, top and bottom, to get our output. Does that make sense geometrically? Okay, now you can start to apply this in higher dimensions, right? This is where things just go from easy to like dumb, impossible level complicated, like that, right? So imagine for a moment that we have, I don't know, 4 columns. What are you doing? My sister, I'm sorry, I looked at the door and she was aiming a Nerf gun at me. Oh my God, it scared me. All right, anyways, so imagine for a moment that we have 4 columns in our data set. So we have
Your attack dog has you, though.
3. No, he didn't. He freaking ran. All right. Yeah, I think he was trying to get behind me. All right, so we got 4 columns. This is terrible. I'm sorry, y'all. You know what? I'm not even going, because I don't have any kind of example that works for this. Okay. Just imagine for a moment that we have multiple columns of data. Okay. And we just very crudely visualize from like a small subset, right? Visualize from a small subset of the data, right? Some groupings in 2 dimensions. All right. So I take the target. All right, and we'll just say C1, all right, or actually I'll just say feature 1, so F1. Okay, so I take the target and F1, and I sort of try to find, some sort of grouping. You guys can stop now. it's like they think I don't know what they think I'm doing. All right. Right. Try to find some grouping. So let's say we're seeing something like this, right? What does this look like? Assume these are all dots, not lines. What does this look like?
2 clusters?
Yeah, it looks like 2 clusters, right? We could draw a line here and separate these 2 clusters. So our input layer is predetermined, right, by the number of features that we have, right? So in this case, we'll say we have 4, right? But it looks like feature 1 to target only needs 2 to split. So then we take a look at the next one. Then I've already kind of screwed myself on this, right? So we'll take a look at the next one. I just got hit in the head with a Nerf dart. F2 and target. Okay. And try to determine the same thing. Is there any correlation here? And let's say we don't. Excuse me one moment, y'all.
Oh shit.
Camera's going down.
Brandon.
I don't understand how now my models are my means are all 1, so it's clearly training off of or fitting off my training data. Oh, I'm so confused.
Yeah, like overfit is your second?
Well, it's a 1-to-1.
Beyond overfit at that point, yeah, there's something.
I was trying today this wrapper, like a classifier wrapper, which you showed us today, but without it, I have a better score than with it, just with adding the layers and not wrapping it in the classifier. Even though I'm using almost all the same parameters besides this grid search and extra parameters, I don't know.
What does that wrapper let us do? Use sklearn for what?
Not the sklearn. I'm talking about the
Create model?
Keras classifier. Like you wrapping your like model. Create model and grid search. You adding into. I mean, yes, using a Keras classifier to wrap the model. But after you using I use the grid search like during the lecture, and I'm getting the worse results with all of this than just using the like regular like without function when I'm just using model and add models and add dropouts, you know.
That's very weird.
I actually did this wrong. All right. Hey guys, I'm back. I apologize. I had to chase my sister. She's trying to get back in my room right now. I can hear her. Yeah, so here's I said to stop. I apologize, y'all. I swear it's not normally like this. It's like this every day. Who am I trying to kid? All right. So, anyways, okay, we need to take. So the first thing that you want to do here is separate your observations into the different class. So to make things simple, let's pretend that we have a binary class, and I make class 1 to be red and class 2 to be blue, right? Then we go in and we make a graph of one feature, any given feature, to another feature, okay? And now we're going to plot, okay, what do our observations look like here, F1 to F2? And I'm going to give a more realistic looking example here. So let's say this is F2 and this is F1. So there's a little bit of overlap here. You can see, right? The one class, blue class here, is kind of overlapping a little bit with red class. But how many clusters does it look like we could make out of this?
3 maybe?
3 maybe. Okay, I'm thinking 2. I'm thinking it's because it looks kind of like, so I'm seeing one little bit here. Here's red, right? And here's blue. So I'm thinking if we cut it this way, we're going to be making some pretty good progress, right? Doesn't look like any more divides are really necessary in this dimension, right? This is sort of the process that you iterate over in your head over and over and over again if you want to try to figure out how many nodes you need and how many hidden layers you need. Okay, I shouldn't have to tell you at this point. You need to do this for F1 to every other feature.
Yeah.
And then, right, and then do it in another dimension. All right, so it's a permutation of all possible feature combinations and all possible dimensionalities. That's 2, 3, 4, 5, 6 to n number of features. Right, so if you have 13 features, you're going all the way up to 12 dimensions. That makes sense? All right, you can't graph 12 dimensions. You just sort of have to kind of think about it, almost mathematically, right? It just becomes abstracted by numbers.
Airplot.
Well, Paraplot will only get you so far. You can view two-dimensional slices, but all the way to n dimensions, you're just going to have an it becomes an exponential number of two-dimensional slices, right? Because you got to take two-dimensional slices of all the 3D objects, and then two-dimensional slices of all the 3D-dimensional slices of all the four-dimensional objects, and then you have to take two-dimensional slices of the three-dimensional slices of the four-dimensional slices of the five-dimensional objects. Do you see the problem here? You're creating an infinite number. It's exponential. Exactly. So yeah, it's really hard to do. The cool thing is that you don't really have to do this, right? And yeah, I was attempting to make drawings, but they're not really working out. So you don't really have to do that. You can kind of go, okay, I've got how many features? So I've got roughly this dimensional I've got this dimensional problem. Let me pick an architecture, right, that looks like it would almost make sense. So when I started my iterations, right, I didn't start with a 64 by 32 by 8 by 8 by 4 by 8. Okay, I did 10 by 10 by 10 by 10 by 10 by 10. Okay, and here's why. I found a couple of features that seem to kind of walk hand in hand. They seem to be heavily correlated. Right, so I did correlation matrix, found that several features were highly correlated. I figured I can reduce dimensionality because of this, right? They're going to carry roughly the same weight and probably have the same or pretty close to the same impact, right? So I reduced dimensionality by by the number of correlated features, and then sort of split where it looks like, okay, you have males between these two ages seem to have higher numbers in this column versus females of these ages seem to have lower numbers in this column, right? So that becomes a new dimension, right? And I just started keeping track of all the different patterns that I'm starting to see. And I did a lot of feature exploration, and then eventually ended up with, okay, I just need a boatload in the first layer. This is what I came up to, right? So I just picked an arbitrarily, what seemed like a large number for the data, right? 64. And I said I can lower that down on the next set because I don't have nearly as much complexity in the next dimension, or rather about half. So I split it in half. So I did 64 to 32. And I said I only have about a fourth of the complexity going to the next dimension. So I cut it down to 8 and then 8. I did 8 again because I had about the same complexity, and then less and then more. Okay, so I just sort of kind of played around with it a little bit. I think I did 2 or 3 iterations before I settled on the one that I did, and it performed pretty well, right? That doesn't mean that that architecture is the only one that's going to work. I could have probably just as easily done a 64 by 64 times 6 layers, and it performed just as well, right? It probably just would have taken longer to calculate. There was no need for me to do what I did, but it was more of an exercise. So what's the moral of the story? It's arbitrary. You can choose the architecture, right? It's sort of loosely dependent on the number of dimensions that you have, but that is kind of a misnomer, right? You can have 3 features and solve it with a simple level, simple perceptron, 2-layer perceptron, right? So it's not a hard requirement to have the same number of layers as you have features. That was a long-winded explanation. Anybody have questions?
Can you grid search nodes of a layer?
Probably. I think you could probably do it with some sort of loop. Be probably just about as efficient as grid search, to be perfectly honest about it. They're not very efficient. Yeah, there are ways to iterate to do a grid search, right? Where you test these, or test this number of nodes, test this number of nodes, test this number of nodes, right? And then have it work. You would supply it in a for loop. Actually, I think there is a hyperparameter for a number of nodes. We don't typically specify it. Hang on.
Adrian, I think you can use the Keras tuner too, but it's like super complicated to use.
No, thank you.
Yeah.
He said no, thank you. Let's see.
During the lecture, we didn't really have time to go to the tuner, like a good explanation with it at least, because we were a little bit running out of time. That's why we didn't have, like, at least by the end of the lecture, I got lost probably. I don't know. That's why tuner is too early.
Okay, yeah, so it's units. You can specify units as a parameter in your grid search.
Even in the 3 brown, 1 blue video, he's like, I chose 16 because it looked good.
Yeah, totally arbitrary. And there's actually a pretty good reason why he picked 16, but I'm not going to go into that. It has to do with the method I just explained. But it's different when you're talking about computer vision, because there's no classes, obviously. That was more for a classification example. But 16 actually works pretty well, and it has to do with the number 8.
I figured as much. I usually try to go off of multiples of 8.
Yeah. It's not multiples of 8. It has to do with the shape of the number 8, because remember, it's doing image classification. Right? So what are your layers doing? Taking nodes from any given sector, right, of an image. So it has to do with the shape of the number. It's
Didn't
weird.
you reveal that it was all random anyways?
What's that? We don't know. So you can kind of sort of abstract a blueprint for how you think it should go, but we have no idea, right?
Yeah, wasn't it like when you actually look into the weights of the neural network, like it's completely
just random. Yeah, totally. That's what I'm saying. You can give your best idea for what it should do.
Yeah.
Right? But at the end of the day, when you click train and run that code, it's going to do whatever the heck it is it does.
Yeah.
Right? It just sort of follows the laws of mathematics at that point.
To where it could never recreate the 9 or the 8.
I mean,
well, obviously there are programs out there, but that one was not nowhere near.
Yeah. Well, that was a really simple example too. Right. But the INNIST digit classification is really famous. There's people out there who've that's been iterated on and iterated on and iterated on. I don't think anyone's going to break new ground on the INNIST data set. But it's a great practice, right, for trying to figure out like different things, getting it to work. And you have benchmarks to compare your results to. Versus something like, trying to program a Tesla to identify pedestrians on a sidewalk versus in the middle of the street. That is not a precedented, right? You don't have benchmarks by which to compare your results to anything else, right? You're breaking new ground there. So that's a little bit different. So you want to train on these methods before you start trying to do something new. All right. Yeah. Like I was saying, you can provide in the dense layer, units is the size of the output space. That's the number, right? You can supply that as units equals, and then that number. You don't it's kind of inferred if you don't supply units, but if you say units equals, you can use it as a hyperparameter to tune in grid search. To answer your question, Adrian.
I see.
Cool. All right. Well, I think we've pretty much covered everything. I mean, this week is mostly centered, I think day 1 and day 2 is more like, how do neural networks work, right? And then day 3 and day 4 were, okay, how do you do this with Keras? Because day 1 and day 2 were stupid hard, right? It was all the math was front loaded on the beginning of the week, right? So we talked about all the math stuff. Day 3 and day 4 is where we actually did, or I think you got an intro to it on day 2 at the end of the lecture, like the Keras model and stuff like that.
And he did it in like 4 lines at the very end of the lecture.
Yeah. Which is frustrating, right? Because you're like, I just spent how long trying to figure out how to take the dot product and doing differential equations? No. And then you just like 4-line it.
I think what's more frustrating is you sit there and hyper-tune yesterday's assignment, the Boston housing, then you can not tune a logistic regression model and it gets better.
Yeah. There's some problems that neural networks just don't do well. They have, kind of a domain of problems that they're good at solving. Right. And then also we've only talked about really one architect or architecture, right? There is a ton of different styles of neural networks out there and papers being written on this every day, right? Describing a new type of neural network architecture.
Well, I could see how neural networks are definitely the future, but you also infringe a lot of freedoms if you're doing live, like exactly like with Tesla. How do you know that Tesla isn't taking those images and storing them in a data bank? Now all of a sudden you're in a Tesla data bank doing something.
I hate to be the bearer of bad news for you, but that's already happened.
Yeah, okay. I know.
Yeah, if you've
we're on public roads, but
I was gonna say, if you've ever put your picture on the internet, anybody can get that, right? It's public domain now. That being said, how data gets used, especially with something like the cameras on a Tesla, is not. It's kind of fire and forget. There is no real use for collection of arbitrarily large amounts of data like that. Like they have so much data already, right? That there's really no use for it. They're not getting any better.
Yeah, but
right?
who's to say that they aren't, like, when your GPS ticks at a certain point?
Oh, they record all your GPS.
Now all of a sudden, the cameras are recording you driving past so-and-so's house.
Well, what do they have to gain from that? That's my thing.
What's the CIA have to gain on anything?
New construction of roads.
Well, it's bold of you to assume that Tesla's giving any information to the CIA, but that aside.
But that's what I mean. Like, now all of a sudden they're driving past your house. Now the CIA doesn't have to have any personal person there. They just know that this person drives past your house every day in a Tesla, and they just activate the camera, watch your house every day at X time. I mean, there's a lot of security.
Yeah, no, there's really, for starters, there's a number of holdups that are going to make that very complex, very hard to do. But it's not. What you're saying is not impossible. I would say just highly improbable.
I think my dad is a chemical engineer, and sometimes he was working on a project with a colleague, and they were joking, and my dad is always TSA pre-approved because he travels a ton. But this project, they jokingly called it a pipe bomb. So they're always sending each other texts about this pipe bomb and how the pipe bomb is going. And ever since that project, my dad is never TSA pre-approved now.
Yeah, no, he's on an NSA watch list because he used the word pipe bomb.
Yeah,
that's it. Yeah, I'm on a watch list as well because I researched how to make an EMP. And I did not know that got you put on a watch list, but now I'm on a watch list. They can't get
electromagnetic pulse.
Yeah, electromagnetic pulse bomb.
Essentially, you would build a nuclear bomb.
No, it's not a nuclear bomb. It's not a nuclear bomb. It's not nearly that powerful. You can do it with a powerful enough radio transmitter.
I mean, that's pretty much all they're using nuclear bombs for now. That's why they're so scared to use them.
Anyways,
they EMP wipe everything.
It does. Yeah, EMPs are pretty devastating to electronics. So I was researching strictly out of curiosity how to make a large, not really a large scale, but like a small scale, personal scale EMP device that could disable electronics within within like 100 meters. Right. Turns out it's not that hard, but because of that, I can't get security clearance.
Just carry around a really big magnet.
So there's logistical problems with that, but I digress. That would be extremely heavy. And also you need an electric current. No, that's not going to work. Anyways, right. So yeah, and a lot of things can get you put on a watch list nowadays and under surveillance. But yeah, man, if you go out, drive around, you see those little like traffic cameras. The CIA doesn't need any help from Tesla to keep an eye on you. That's all I'm gonna say. The fact of the matter is, though, anonymity comes from the fact the sheer numbers of people that they're observing, right? Like we observe the whole sun, but we don't know what's happening to every single particle, right? You can't. It's just one of bajillions, right? So it's kind of abstracted away. Same sort of concept. They can develop a machine that keeps an eye on you, but personally, I don't care if a machine keeps an eye on me because I ain't doing anything that's, like I got to worry about. But that's just me.
Stepping stones, man.
Yeah, no. I'm fully aware of the threat of privacy invasions, right, and the precedent that it sets. But we're not going to have that conversation.
Can you imagine a world in which privacy exists? Like, I feel like it's impossible.
It kind of is.
It no longer does.
But it never really did. It never really did.
And it's just it's like we're privacy, kiss it goodbye. We need ethics. We would just really hope we have decent ethics to deal with the fact that
we need yep, exactly. We need ethics around how we use the information that we collect about people, because there's almost no way to avoid collecting information about people. You almost have to in some cases, but so I mean, take that for what it is. I don't really I don't feel like I would really want to argue the semantics of privacy and data privacy, stuff like that.
I mean, it's a real. I'm surprised we don't necessarily talk about it though, because it is. We could end up getting a job, and being privy to information that we shouldn't.
What do you mean?
I mean, we're training to be data scientists, and who's to say that we're manipulating data? They can strip certain things and give us encoded data that might be stuff that we shouldn't have, There's definitely some legality to be wary of.
If you're working with data that's been anonymized, I can never say this word right.
We've worked with
anonymized. If you're working with anonymized data, there's nothing you can do about what that data is, right? You don't know. It's the whole purpose of that is so you don't know. Then if there's any issue with the ethics involved with the collection or storage of that data, and it's real in its true form, it's not on you. It's on whoever collected or stored it, right? That's not something you have any control over. So I would say keep your concerns and your worries in the range of things you have control over.
It's true.
In that regard.
Gotta get a job first, right?
If you get a job and they're messing with shady data, there's a number of issues. It didn't start with you. They were probably there before you showed up, right? It's nothing you would have any control over, right? There's no way for you to know that that's data that they shouldn't have, or that you shouldn't have.
I mean, there's just a reason why a lot of data science jobs have security clearances.
Yeah, well, of course there is. You're dealing with private data. That's just the nature of, people are protective over the things that they know.
But what I'm saying is, like, it's not necessarily our job to know what the data is, but it is our job to make sure that data isn't leaked as well, or that we're not manipulating and sending out data that shouldn't be.
Well, yeah.
You know, there are ethics behind data science.
Okay. Yeah. No, in that respect, yeah, absolutely. What you do with the data is absolutely on you, and good ethics definitely is something that you want to practice. For sure.
Okay, I have a question about like whatever we're doing right now. Today's assignment was just to use everything what we learned so far. But to check myself, I just used the random classifier without any parameters or anything, just like everything default. And next one, I use everything like this Keras model, some layers, and I'm getting the same score. Like, what is the point? Why? Like, is it something wrong with my models? Like, I think it has to be like much better score than just regular random classifier.
No, there's no reason why it should have a better score than a random classifier.
I think the data is too simple.
Random forest. Yeah. I mean, if the random forest classifier, remember the random forest classifier is, it's not a lightweight model. That's a very, very sophisticated model. It's been around as long as the neural network, if not longer.
Did anybody get more than 80% accuracy score? People?
I don't think so. Now with the diabetes data set, no, I highly doubt it.
Not the diabetes who are working today on this telecom church thing. Telecom.
I saw people that got way worse than that.
Yeah, I'm still getting on my grid search stuff. I'm still getting standard deviation 1. No, 1.
Oh, 1. Okay.
I got 74 at one of them, and I'm still waiting for another model to run.
Yeah, I keep rerunning it.
Yeah, I've been waiting for like at least last 30 minutes, and it's still running.
That might be too long.
With your grid search, you might have too many parameters in your grid search.
Yeah.
Okay.
With my grid search, I'm not getting also not more than 79 and 6. I mean, 80% is like maximum.
I stopped running more than 20 epochs on that.
You have to consider also that just because you have data does not necessarily mean that there is any guarantee that there is a model out there that can, get a certain level of accuracy.
Data was very messy. I was thinking maybe I just didn't do enough cleaning and stuff like that because
that's a possibility.
I was thinking it's just going to.
But if you're getting 79% on your validation, you're actually at the higher end of that score.
I was just thinking that it's because we were getting really good results today during the lecture with different data sets, but it's probably just
some data sets. Yeah, some data sets you can just get really good, scores on. Some data just it's not there. You can't do it, right? With the diabetes data set, there's so much overlap, right? There's so much noise that you can't get but a certain level of accuracy there, and there's certainly no way you're getting 100%.
That's good to know. Today I will go to sleep then.
Yeah, so I'm saying work on the implementation. Don't worry so much about your score. Okay, it's not a competition right now. It's
but
sure that you understand.
I'm trying all of the different parameters, like hyperparameter. I was changing a lot of stuff just to see how data how it's reacts, like how my model behaving. I would say that's why it's important for me.
Okay, I mean you can change it, and I want to make clear that you can change a lot of parameters, and it could be that none of them have major impacts on how your model performs. That's a thing that you might run into. Okay, that's a real situation. So just majority class is 73%, and you might not be able to predict much better than that. So that's something to consider, right? All right, cool. Well, guys, if it's all right with everyone else, I would like to hop off a little bit early tonight. I didn't get a lot of sleep, so thinking about crashing.
Right, of course.
Thanks, Brandon.
Yeah.
Thank you.
Okay,
You
thank
got
you.
it. How's everybody feeling though? We feeling pretty feeling good for the sprint challenge? Like everything that we talked about today, implementing the Perceptron with Keras and being able to
create the hidden layer for a multi-layer perceptron and doing hyperparameter tuning. That's essentially what your sprint challenge is going to be. Feeling pretty good?
Yes.
Yeah.
Tomorrow morning when we see assignment.
Yeah.
Yeah.
You guys are sitting and be like, oh man, this is it? This is all I gotta do? Okay, no problem.
But sleep well, dude. No Netflix.
Yeah, no more Netflix World War II documentary binges for me. I only got an hour of sleep. I don't even know how I'm conscious right now.
All right.
All right, yeah.
What?
I'll see you guys tomorrow.